Hi, today we will cover Transformers, the engine behind today's most powerful generative AI models. So, for this, we are going to follow this outline, and mainly we will start with attention mechanism. So, overall, we're going to understand attention, self attention, multi head attention, and this is going to allow us to understand the transformers architecture, okay? So in order to introduce the concept of attention now, it's useful to begin with a very simple example from reading comprehension, okay? So when we human try to read, let me say, a short paragraph and then answer a set of questions, mainly what we do is that we do not process every sentence with equal focus, okay? So remember the reading comprehension exams that you had in primary school, for example. What you do is that you read your question, and from your question, you try to get some keywords and you try to search that keywords in like the text. And usually we pay more attention to that paragraph containing the or sentence that contains the keywords, okay, which is relevant to the question, okay? And this is how we try to answer. So this kind of selective focus allow us to extract the information needed in a kind of efficient way, okay? So the same idea, let me say, that scales to much larger context that we will cover today. So let's stay in the context of humans and how we humans think, okay? So to answer a question about, let me say, of a long book, what happens? So do you mainly read the whole book, let me say, and give the same importance to every sentence and every word in that book? Absolutely not. Okay. So the idea is not if I ask a question about a book that you are reading, you're not going to reread, sorry, the entire text. Mainly how we humans do, we would kind of tentatively return to the earlier chapter if the question is concerning the, let me say, introductory things or things usually happening in the start, okay? So because we know the information of interest must be located there, okay? So this is the idea. In other words, how our human brain works, it usually, or let's say it automatically identifies which part of the input deserves, let me say, more attention. And that mainly depends on the task, okay? So a similar strategy here applies when we maybe work with a scientific paper. So the idea is that we do search for the motivation, let me say, of the work. Do we search about this motivation of a given paper that you might be reading in the experimental results section? Absolutely not. We don't search for motivation in the experimental results because we know that such information is typically introduced in the abstract or in introduction, okay? So likewise, when we look for related work, so naturally we move straight to the related work section or literature review section, okay? And in this section, usually authors they summarize existing approaches and their limitations, okay? So this is the idea is how do we mainly pay more attention to some specific um, parts of text or document or the book that we are dealing with. So the secret, I would say, is in allocating our attention accordingly, right? So now, this example is going to help us build an institution needed to understand the attention mechanism that we will cover today. Okay, so this attention mechanism is mainly used in modern deep learning approaches or models, where let's say attention plays a central role in tasks like, for example, machine translation, okay? In machine translation, like the system must usually generate a sentence in another language, okay? And there is a constraint, is that the model must, let me say, preserve the meaning, okay? And also the structure of the original text, okay? So let's take a well-known example of machine translation. Here we have Google Translate, okay? And so here, given the input, so he loves to eat, what happens? There is like a target language, okay? Here it's German. And now, behind this capacity and this final result that we see, liebst, like S to Essen, which is a translation for he loves to eat. Now, what is the secret behind? So behind this capacity lies the attention mechanism, okay? And this attention mechanism enables the model to identify, let me say, which parts of the input sentence are most relevant, okay? And this mainly when it is going to generate each word in the output, okay? So instead of processing the entire sentence with the same importance, I would say, or uniformly, let's say. Okay, so the model, what we will do is kind of dynamically focuses on specific words or phrases that contribute to the like next output token. So this idea or this selective focus significantly improves the translation quality and forms, let me say, the foundation of modern sequence-to-sequence architectures such as transformers, okay? Now, so what we have is that, let's say we are understanding the general institution behind attention. What we can do, let's say that we can look how online translation systems like they operate, okay? So modern translators rely on deep learning, and we say that deep learning is changing everything. So let's say like this, I would say big changes are deep learning is behind them. So, but when we talk about deep learning, we have a lot of architectures and models, okay? So in particular for machine translation, the model that I would say um, uh, is the model which is used in this case is known as the encoder decoder like architecture, okay? So this is mainly the, I don't know if you see my cursor or you don't see, so let me just try to show you with the laser pointer, okay? So this is the encoder decoder architecture. What we see in the encoder decoder architecture is like here we have the sentence, the input sentence. This input sentence is going through the encoder. But before that, there is here some embedding, okay? So the idea is that if I have he loved to eat, input sentence. So this, as you can see, is a text. So it's natural language, it's plain language. It's written like we have different letters, we have spaces, we have like characters and so on. So how to fit this to a neural network? Mainly, this is the problem. So we cannot do this. In images, like for example, we have pixels and pixels, they are having values, numerical values. In this case, we don't see any numerical values in text. So how it works? This is a very important question. So we have this layer before the encoder, which is the embedding. The idea here is that we are like going to transfer, the encoder is going to transform the input, okay, into a compressed representation, let's say. But before that, so it's not mainly going to work given the input. It's going to transform mainly the numerical representation of the input, okay, which is called the embedding. And this embedding is also known or called like encoded vector. So the encoder is going to consider the input, not the input, is going to consider the embedded representation of the input. So here we are going to have numerical values. From these numerical values, what will happen? Like the encoder is transforming into what we have here is a fixed size vector. Okay, so the fixed size vector now is having, I would say, some problems in this case. Okay, so let's discuss them and let you also think with me what could be these problems. Okay, so the idea is that what we have or what we do is like we have a sentence and we want to translate the sentence. What we have the architecture. The architecture here, it has two main parts, the encoder and decoder. The encoder cannot straight process, I would say, or work with the input sentence because it's written in a natural language. The idea is that we do the embedding, means encoding, writing in a different representation. How we do that? Did you ask this question to yourself? We mainly use RNN, recurrent neural networks, or also LSTM. So these architectures allow you to embed the input sentences. Just examples, okay? Now the idea is that no matter what, or let me say regardless, the original length of the sentence, what will happen? What the encoder is going to do? The encoder is going to map it into a fixed size vector, which is S in this case, okay? So this vector is mainly acting as, I would say, the entire input, okay? And mainly it captures the essential information which is needed for translation, okay? So this vector S is often referred as the hidden state. And now, once this hidden state now is obtained, what will happen? So it will go through the decoder, okay? And from the decoder now, what we'll have? We will have the results of the translation, okay? So in all this process, so what we have the idea or the process is summarized as follows, okay? So just in color. Okay, so we have mainly encoder, okay? We have this representation S, which is creating some problems because it has a fixed size. Then we have this decoder part, and this is giving you the final translation. Okay, now the idea is that in 2014 there is a paper that I keep for you the reference. Okay, so there is a paper that has been published in NeurIPS, and so let me tell you just that NeurIPS is mainly one of the top AI conferences. So this encoder decoder architecture has been published in this in this conference, and this paper mainly is considered as landmark. Okay, so the idea now, or the main challenge, or the problem, like I shown you, is there are limitations related to this paper or this published work. Okay, and this is mainly opposed by representing an entire sentence using a single fixed vector. Okay, think of it when I say an entire sentence, like 80 for example tokens or words. Okay, so this is a huge constraint, and this make it difficult for models to capture information from longer or more complex sentences. So it makes it really challenging and difficult. So, and the attention mechanism now is introduced in this context, okay? And why? The reason is mainly to overcome this bottleneck. And this attention mechanism allows the model to dynamically, I would say, focus on different parts of the input during the translation. So this development laid the foundation, like I mentioned in the start, for modern translation system that we are using today. Okay, so now let me examine the main limitation of the original encoder-decoder model. Okay, so the use of a fixed size representation. So the idea is that now the encoder, how it works. The encoder, like I say, it compressed the entire sentence into single fixed like dimensionality. And this is mainly regardless, like we don't care about how like the how long is the sentence, okay? So in all cases, it's going to be like compressed in like that vector S, okay? So if we have short sentences now, this is typically mainly okay. So there are no problems. Like he loved to eat, it's a simple and short sentence, so that's okay. Now the problem is, like I mentioned, when we have let me say longer or more complex sentences. So here there is a difficulty that arises. Now, if the sentence grows in length, or if we attempt to encode entire paragraph, or imagine even if we are encoding a chapter, okay? So the idea here, capturing the relevant information within one fixed size vector becomes increasingly challenging, okay? So an important detail here may be lost, okay? It can happen, right? So if the model is going to compress things, so when I say things, it's a large amount of information into a limited space. So this will absolutely result in losing a lot of details. So this constraints mainly kind of fundamental weakness of like early RNNs based or LSTM based encoder decoder architecture. Okay, so even though RNNs can technically, I would say, process like sequences of variable length, so they do, representing the final output using a kind of single summary vector limits the model's capacity to handle longer range. Okay, like if you have more dependencies, and so it would be even difficult to maintain, I would say, fine grained like a grained information. Okay, so the idea now is that the primary issue is not the input length itself. So it's mainly the fact that the entire input, and that is regardless its size, must be encoded into one fixed size or fixed dimensional vector. Okay, so this is mainly the bottleneck, and this bottleneck becomes mainly like more serious when the sentence becomes longer. Okay, so this makes it difficult for the model to produce high quality translation. Okay, now, so the problem becomes clear when we look at these plots. So what we see in these plots, so but before moving to these plots, let me tell you that before, when we had like when we deal with vision models, like for example CNNs or machine learning models, let me say, what we do is that we assess or we evaluate the performance of the model. Okay, so how we do that? Usually we use metrics, okay, to quantify and evaluate the end results. So metrics that we use in CNN, for example, or in neural networks. So we mainly use it accuracy and validation accuracy, training accuracy. We also use loss, validation loss, training loss, robustness, and so on. Okay, and what we do is that we plot these like metrics, and we always try to fine tune the model. We wish to have always the best like curves and so on. Now this is in vision. When it comes to language, we have, let me say, different metrics to evaluate the language models. Okay, so one of these like metrics is the blue score. Okay, so what we see here is like, for example, on the x axis, we have the length of the sentence, okay? So here we have shorter like sentences, like length, like 0, 10, 20, until having longer sentences like 60, 70, 80 tokens, okay, or words. In the y-axis, we have the blue score, okay? So what we can see now is that, let's say, the blue score here especially, okay, so drops dramatically, okay, whenever we have longer sentences, okay, so this has a meaning, okay, and so this shows even that classical neural networks approaches, they struggle when we have this problem of longer like uh, sentences, okay. So now the question is, why does performance drops? It's a very logical question, okay? So we see clearly that for long sentences, they mainly are the problem. Long sentences are the problem, okay? And we need to understand the reason behind this before moving forward. So the issue here becomes clearer. So when we look at how sentences like length affect performance, a shorter answer or comes like, for example, here we have he loved to eat, and this sentence after being embedded, it's encoded, and then the encoder is like compressed, like the result of the encoder part is the compressed version or the S vector, the vector we denote by S here. So the problem in this S, because it has a fixed size or it's a fixed size like length or vector, and it lacks, let me say, sufficient capacity to capture all relevant information for long sentence. Okay, so if this is the problem, and this is mainly the reason behind the drop of in blue scores. And the problem is that, like, we are mapping, let me say, the input into a fixed size vector. Even that this input is too much long, so this affects the blue scores and decreases, I would say, the blue scores. So this mainly also proves that typical approaches in deep learning, like RNN and LSTM and so on, like they have, let me say, limited or poor performance when it comes to long sentences. So we're understanding the problem. Now, what we need to understand why, and it's clear. Okay, so just I was recording before this one, but I was not sharing my screen, and now I was explaining the whole lecture and now I'm recording again. So this slide mainly I was reserving it to explain the difference between like mainly what happened when we have the fixed size input, okay, or the varying size input, okay. So usually in language, so far we have good experience with language, and in language like in CNNs, what we have is, I don't know why I was. Okay, I will explain step by step because, okay, so in language, if I have a model, I usually have a data set, and the data set is, in vision is images. We usually like dealt with MNIST data set, which contains images of fixed size of 28 by 28 pixel, okay? So why I'm saying this? Because this is the input. And the input in these kind of approaches is fed into a neural network. So one of the question is, if I ask you, now we have a neural network for image classification, and we know that we will work with the MNIST, how, my question is going to be, like how long or what is the dimension of the input layer, okay? So the input layer here, so has how many like neurons? The answer is simple, okay? So before moving to the different layers, we can have convolutional, we can have dense layers, we can have pooling layers, we can have whatever we will have. And at the end, we will have our output, okay? So now the question, if we focus on this input layer, first one, the dimension or the shape, it's mainly the shape and dimension of the input images. So if I have this image representing, let's say, number 0, and it will go through the network. So it will go through this layer having the dimension 28 by 28, same like the image, okay? So now the idea is that I can have a different sample, okay? Think of it here, I have different image. In language, I have different sentence, okay? So I have a different image, like say, for example, number 1. So number 1 here is also having the dimension 28 by 28 because your data set, all your images, they have the same dimension, right? So if you don't have 28 by 28, there will be an error somehow, okay? It makes sense for images because we can even pre-process the images if they don't have even the same like length and the same dimensions or shape. So we can resize, we can do many things. Now the problem is in language, okay? Think of it, if I have many sentences, some sentences are short, some sentences are long, and I'm going to feed, let's say, to the encoder part. So it's not like possible, let me say, to cut, let's say, this sentence or resize this sentence, okay? So this is mainly the idea, okay? And so the situation in NLP is completely different. And here the sentences like can naturally like vary in length, okay? Which makes sense, which is very normal. So in this case, what happens when we have the sentences like varying in like length? Short sentences are fine, are okay, like he loves to eat. There is no problem for that. Now, when the number of words increases significantly, like this is a problem. The model must handle much longer, I would say, time dimension, okay? So this leads to like two well-known issues in RNN. So in RNN, we have the first problem, which is vanishing gradient problem, where the information like fades over long sequences. And the second problem is related to model depth. So in traditional neural networks, the rule of thumb in this case could be used, and like that, it says that deeper networks take longer to train. For RNNs, like depth corresponds to the length of the sequence, because each time, like step, it like acts like another layer, okay? So longer sentences now effectively create deeper, I would say, unrolled networks. And this mainly makes training slower and more difficult. And also it can lead to losing information across time, which is the main challenge. Okay, so with this understanding, like the problem becomes clearer. And so it's also simple. The long sequences, they create long time dependencies, and the fixed size encoding cannot like capture all necessary information in this case. Okay, so just to clarify things. Next, now we have a problem, and the problem is clear. The problem is due to this fixed size, like I would say vector. And if we have a problem now, we know that the problem is here, okay? So in the literature, whenever a limitation appears, there are new methods that are proposing kind of solutions or like ways to address this problem. So if the fixed site representation now is a problem, the idea behind attention was here introduced as a solution. So instead of forcing the model to compress, I would say, entire like long sentence, for example, okay, into a single summary vector, which is S, and this one is maybe becoming unreliable for long inputs, okay, the attention mechanism simply removes, I would say, the need to use this vector itself. So there is a problem. Let's remove this problem. And so what we will do if we are not going to consider this vector, okay? This is the main question. If we are removing this vector, how to do? So we maybe need to summarize everything. We don't need, sorry, to summarize everything into a fixed size like vector. And in other words, like we avoid this bottleneck entirely by simply not relying on a single vector summarization. So if there is a problem, just avoid this problem. If there is this vector is making a problem, let's not use it, okay? Let's use the attention mechanism instead, okay? Let's see how. So we'll continue using, okay, the full long like sentence, okay, we'll do that. And we like fall back into, let me say, the same limitation as earlier. So the issue becomes unavoidable in this case. What happens? So if we rely on traditional like summarization approach, we will fall again into, I would say, like fixed size vector, okay? So instead, like have the encoder pass all inputs, hidden states to the encoder to decide which to use for prediction at each time step, okay? We can think of it, but there is a problem. So the idea is that we will use the attention mechanism, okay? So now the idea, like I mentioned, is to use the attention mechanism, and it's not a problem to have long document. It's not a problem to have many pages or even like thousands of pages. Now, why it's not a problem? Because we naturally focus only on the relevant parts, okay? So it mainly inspired by the example I given in the start, how we humans pay attention to things, okay? So, and the question now, if I have a book and and someone is asking me a question. Now, if the question is about the beginning, okay, what we will do mainly? Automatically, we're going to check the first chapter. If the question being asked is concerns the main story, okay, we maybe concentrate on the middle. And if the question, let's say it's about the end, for example, okay, or the conclusion, we focus at the end of this book. It's the same, it's exactly the same thing. So the attention mechanism follows exactly this principle. So it preserves, okay, performance on long sentences by allowing the model to focus on most relevant segments instead of compressing everything into one summary, okay? So we still need to handle long inputs. That we have the size is okay, long, no problem. But with attention, we no longer rely on single fixed vector. Like to implement this idea within encoder-decoder framework, mainly two approaches are used. The first one is known as the hard attention, okay? And we also have the soft attention. Let's focus on the hard attention. So hard attention, as the name suggests, it selects one specific token at each time step. The target now word depends mainly on one input position, okay? And now, let's say what we have here. We have, this is the target, and it has 4 tokens, means 4 words. For each time step, what we have, for example, er is the translation for he. So the focus is here. This verb is for love, this verb. Like this, like for to. And essen verb is for eat, verb. So the idea is simply like we are treating this sequence like at each time step there is a focus on like something in the input, a token from the input. So now since training neural networks relies on back propagation, let's say, and the gradient-based optimization, because you know that we went through all these details of training neural networks. So what we need, maybe we require continuous and differentiable like operations. And now if I am like for each time step t, I have kind of discrete like things. Now this is mainly a problem, okay? And if we use this, like we keep focusing on the input and we use this hard attention mechanism, so we have this problem, okay? So first one to summarize is like the idea of focusing uh, on a single input token, okay, at a time, like at a time. This is giving the first limitation. And the second one is due to the like differentiability of the process whenever like we are trying to apply backpropagation gradient optimization and like things related to neural networks like um, training. Okay, so here hard attention does not meet this requirement, which becomes here a major drawback. So what maybe like we can conclude like just limitation. A target word relies on information about one input word and hard attention is not differentiable. So these are the limitations of hard attention. Okay, so as a solution now what we have is we can use the second option, which is the soft attention. Okay, and how it works. Soft attention mainly computes a weighted combination of input tokens, and this means that at each time step the model like assigns different levels of importance, okay, to the words in the sentence. Okay, so now if we see like this is the first time step, instead of considering all the time steps and one by one like in the hard attention, what we will do, I will focus only on the first time step and I will think of all the input tokens. Okay, and for each of these tokens there is an importance, like here you see the more importance it's for he. Okay, and now for example, okay, now this is for the first time step. For the second time step we do the same. Okay, so what we will have, we will have different, I would say, distribution. So the model will naturally assign, let's say, higher importance to the second word in this case. Okay, and since this is why maybe it's like it like the current position in while processing. Okay, so at the same time it still gives like some importance to, like for example, the previous and the next words. Okay, but in this case with fewer like like in this case lower weights. Okay, so next for the third time step we do the same. Okay, the same at each time step, so the model adjusts these weights again and again and identifies where the next like important like information lies and assign attention accordingly. Same for the fourth like time step. And in this way, so what we obtain is a distribution. Okay, so we mainly obtain a distribution of weights. Okay, and so the idea of this distribution of weights, or let me say different levels of importance at each time step, so this is the essence of soft attention. So it introduces flexibility, and that is by allowing the model to, let me say, focus, okay, more strongly on kind of a specific parts of the input at each time step. Okay, so and this is maybe the focus that is giving to a particular part is rather than like relying on fixed or single fixed summary. Okay, like in the hard attention. And so now this is like the distribution. And so we are reaching now an important question. Okay, how should weights be chosen for each input? This is very important. Okay, so the idea is clear. We try to explain the idea, and in this example, like at the fourth time step, for example, what we have, the most important like weights are there, okay? And also we have, for the word he also, we have, let's say, important weights, okay? So here we have the two most important words are he and it, okay? Which makes sense in this sentence. So uh, he loved to eat. He is a very important part. It is also very important. So how these words are actually calculated? Okay, they make sense for me now, but let's understand. So how do we decide that at a given time step, like certain words, like should receive, let me say, more or like higher or lower attention, okay? So what exact values should these weights take, and how do we select them? Okay, all these are very important question, okay? And one possible idea or answer is to manually introduce what we call linguistic knowledge, which means like we're going to mark verbs, mark like subject, mark the object, like this way. Manually, we are going to mark the linguistic knowledge, okay? The problem is that this approach, it will become at some point unpractical, okay? And let's say machines do not like inherently understand grammatical like categories and manually annotated, I would say, like manual annotations of every token, even it's not possible or scalable. Especially that if you think of it from um, the growth of the vocabulary perspective, or the variety of languages that we have, or even the sentences, structures, and so on that are at some point can become more and more complex, okay? So rule-based or handcrafted annotations, in this case, mainly become ineffective for large scale problems, okay? So now, the idea is that I would say, similar to neural networks in general, the model must learn these weights automatically. So this is the key, and this is the most important part. So instead of hard coding or manually specifying importance, the system learned to correct attention distribution from data experience, okay? It's because mainly learning provides, I would say, a more robust and scalable way to introduce knowledge into models. So the key is in learning. So this is the core problem. And the solution is like we propose to learn the attention weights. Why not? Okay, so previously when we talk about weights in neural network architectures, mainly we follow the, like you are familiar with the process of training a neural network. First of all, we initialize some weights, we perform the forward pass, we compute the loss, okay, and then we apply the back propagation, okay? However, or for now, what we have is attention weights are not learned exactly in this same way, okay? The concept is similar because we still learn from data, but the mechanism is different, okay? So to address this, the architecture that you can see here was introduced in the literature, and specifically to learn attention distributions, okay? So this architecture is very famous. And so first, as always, that, like what we do is we begin with the encoder, okay? So here we have the encoder that produces hidden state for every input, okay? So now let me ask you maybe like how many tokens do you have in this like in this like input? Hmm? So think of it. So how many, I would say, so we have four, okay? So for four words, let's say, okay? And for each of them, what we'll do at the encoder level. So we are going to produce the hidden state. The hidden state is mainly what? The hidden state is mainly we're going to use kind of an RNN, LSTM, in order to move from that text to some numerical vector representation, okay? So here each of them is represented like, let's say for values, like numerical values, and this is the size of the encoder hidden state in this case, okay? Okay, so we have 4 time steps, okay? And corresponding, let me say, to 4 words, okay? So we must compute the attention weights for these 4 tokens, okay? So the attention weights now is the second step. So what will happen? We're going to take this as input of the decoder, and attention weights at each time step here, like what will happen? We are going to evaluate how relevant each input word is to current output, okay? So this comparison maybe needs like some measures that we're going to discuss so far. But now let's focus only on the overall architecture, okay? So the third step now is from the second step, we have for example, for each decoder time step, attention weights are computed and determine each input's relevance to the prediction. Now, from this information, which is the relevance here, I mean correspond to the importance. And when I talk about the importance, I mean which parts of the input should contribute more strongly, let's say, to the final prediction. So the third point here is at each decoder time step, a prediction is made based on the weighted sum of the input, okay? So we use the weighted sum of the input representation, okay, given these scores, okay, in order to obtain the output. Somehow here we perform some probably concatenations or combination, I would say, of obtained result, and based on when I say obtained result means the learned attention weights, okay, and this mainly leads to their learned attention weights that mainly give you or lead you to the final output, okay? So now we will examine or go through this architecture in details, or let me say step by step, okay? Starting with the encoder. So we'll see how it works at this level. So what we have now is a sequence of words, okay? So you have x0, x1, x2, and for example, until xi, okay? This is our sequence of words. And what we want is that we want to encode this sequence of words, okay? We want to obtain at the end the embedding or the encoded representation, okay? So one way to do this, or one common approach, is known as the bidirectional RNN, okay? So you can read more about bidirectional RNNs in this reference, okay? And this link, it's you can go through, but let me summarize it quickly, okay? So bidirectional RNN mainly consists of 2 RNNs or 2 LSTMs, okay? One processing the sequence forward, like you see here from S0 to SI, okay? This is a forward processing of the sequence, okay? And the other one here processes the sequence, okay? Let's say it's backward, okay? In a backward way, okay? In the opposite direction, okay? What happens then? Their output is concatenated, okay? And this concatenation is resulting into a single hidden state. Okay, so here mainly let me say that the main advantage of this like kind of structure is that RNN carry memory. Okay, and for example, if the sentence is let's say begin with Teddy is this is the sentence and the example that we are considering. Teddy is and then we don't know what will come next. So here the model is going to keep memory of the word Teddy, okay? And it can predict like what might come next, okay? So perhaps it could be beer or even the name of a person. So the more information the model has about the past, okay, the better it can predict the future. So this is one of the strengths of bidirectional architectures, okay? But like any method, let me say, they also have their own disadvantages. So the main disadvantage here of this like bidirectional RNN is that we need to access to the entire sentence in order to make the prediction, okay? And in attention-based methods, the full input sentence is already available. But with bidirectional RNNs, this like requirement becomes limitation. So if part of the sentence is missing now, as in our earlier example, like Teddy is okay. So we have that part which is missing. So the model cannot determine which word is correct or most accurate, and it must see the whole sentence to make, let me say, a reliable prediction. So in this context, let's say that two architectures were developed or published. So one of them is shown here. So in this paper from ICLR published in 2015, again, this is a top AI conference. So what we have here, it's like the architecture, okay, neural machine translation, the name of this paper, okay, and it's Barndo's neural machine translation. So this architecture is published in this paper, and the idea is that it illustrates that the encoders at the encoder stage, what we can do, we can use this bidirectional RNN. Okay, so the encoder relies on this bidirectional structure while integrating the attention mechanism. Okay, this is just let me say related work. Then there is another work, and this one, like you can find again in this link. So it was proposed afterward to further improve the results, absolutely. So this architecture here so shows like what we have is, so it's the Luang's neural machine, and what we have here is kind of, here we can see two layers, okay? But the idea is that the key difference is instead of using the bidirectional RNN like previous one, we introduce what they call multiple stacked layers, okay? So we have many layers in this case, and it began with two layers, let me say, then the model like went like deeper, or they are increasing the number of layers later, okay? So this deeper structure, let me say, it helps to enhance the overall quality of the translation, okay? So now we have another like solution, but mainly it's inspired by the previous approach. So here Google maybe was like inspired by this approach and extended, let me say, significantly. So in 2016, you can find in this like again paper, like what they did, they increased the depth of the model from just 2 layers to 8 layers. Imagine, okay? So here we have 8 layers. So instead of what we have like shallow encoder, they used much deeper one. And let me say, all of this is simply another way to embed the input, because it's creating problem how to embed the input in an effective way. So these variations are different methods, and as you can see, so different ways for encoding the sequence, but the idea remains consistent. So we pass the inputs through multiple layers to capture richer representation, and this design is known as stacked RNN. So where several blocks or layers are placed like let me say on top of each other. The idea here is mainly to improve the performance. Okay. Now, let's dive into the details of the first block. So earlier I maybe talked and focused on the point of how many inputs do we have in here, okay? And the answer was maybe 4, okay? So these corresponding, like, let me say this, if we have 4, like the number of inputs, it means that we have 4 tokens in our sequence. So this is the sequence and it has 1, 2, 3, 4, 4 tokens, okay? So which means that we are working with 4 time steps, in other words, okay? This time step 1, time step 2, time step 3, and time step 4. So now how does this process mainly works, okay? So this we are mainly understanding, okay? Let's move forward. So suppose now that we have our input already embedded, now done. And from this input now, there's no problem in these embeddings right here. So what we need to focus on maybe in this decoder part, okay? And given that we already obtained the encoder hidden state, okay? So once these hidden states are produced, now what will happen? Okay, so we will move to the next level, absolutely. So the next level at each now time step, at each like decoder time step from these 4 time steps, what will happen is that we are going to compute some metric, okay, which is the similarity metric, okay? And the similarity metric here is going to be computed between 2 elements. The first one is the decoder like hidden state, which is this one, and in the other hand is the encoder hidden state, which is this one. So this like metric is, or computation, is going to result in a score, okay? So this is mainly the idea, okay? So once we have these scores, from where mainly we have them? We have them by using or by measuring the similarity, and this allows us to generate these scores. And this similarity calculation mainly is performed, like I mentioned in the start, for each time step. So this is for the first time step. We mainly do the same for the second time step, for the third time step, and for the fourth time step. Now what we obtain is that we are obtaining 4 scores over here. So 1 score we have for each time step. Okay, so there is a corresponding similarity like score for each of these time steps. And now the question is, how do we measure this similarity, okay, in order to obtain this value? So these scores, we say that we are measuring the similarity for each time step between these 2 components, the decoder hidden state and the encoder hidden state. Now the question is how we measure this, okay? So as you remember, many machine learning methods maybe rely on similarity. For example, in k-means, or what we do in k-means, mainly we measure a similarity to the centroid, okay? In, for example, KNN, the K nearest neighbor, what we do is mainly we select the closest, I would say, neighbor and compare distances. So if the distance is minimal, like we assign to that class, okay? So the concept of similarity is very important, and let me say central in many machine learning models. And here the similarity gives us a correlation between the decoder hidden state and the encoded input, okay? Or the encoder hidden state as well. So now the representation, let me say, okay, we have this way of represented mainly as an encoder hidden state. So this course, let us, I would say strongly, how to say this? This correlation gives us the idea about like how strongly the decoder hidden state relates to each of these four like time steps mainly. Okay, so the idea is mainly the correlation or the relationship, I would say the degree of this relationship between the decoder hidden state, okay, and each of these time steps. Okay, perfect. So how do you actually compute this? This was the question. And the goal is to measure the similarity or correlation, like I said, between the decoder hidden state and the decoder hidden state and each of the encoder hidden states. So what we do, or mainly in practice, so this involves, I would say, applying mathematical like function, okay? And this mathematical function mainly quantifies how close I would say these two vector, okay? So mainly this is what we call an attention function. And there are several ways proposed in the literature to like measure this similarity, okay? And we will review them briefly, okay? So when we decide, after reviewing these like three, I would say, existing already like possibilities, we are going to know the advantages of each of them, okay? And this is going to allow us decide which of them we are going to use, okay, for measuring the similarity, okay? So let's start with the first one, okay? So the first method, this one, okay, is the dot product, okay? So this is the dot product. And the idea of dot product, mainly it measures the similarity by what we do here is we multiply the elements, okay, of these two vectors element wise, okay? What we do, like for example, the first one multiplied by the first one, the second one multiplied by the second one, the third one multiplied by the third. And what we do is that we sum these results, okay? So this first one multiplied by this first one plus this second one multiplied by this second one, third one, plus, and so on, okay? So this is the dot product. Another method, just we're going through them quickly, is the bilinear, okay? So for bilinear now here, the idea is that we apply, so if you can see here, so you have something different, like we didn't have here, which is this matrix, which is the weights matrix, okay? So this weights matrix is coming between the two vectors, okay? And it, let's say, essentially like treat the similarity function, we can think of it as a small neural networks, because this matrix is of weights, okay? So now the third option is to use multi-layered perceptron. And when we use like multi-layered perceptron, the idea is that what we introduce in this case, okay, so we are going to follow this formula, which maybe introduces the nonlinearity via this kind of activation or let me say transformation before producing the similarity score, okay? So these are like three existing methods which are used in previous works to measure the similarities. Still, our question is which one we will focus, okay? What model parameters like must be learned when using the dot product? We start with the dot products, and by answering this question, probably will be conversion towards the final response. So, what model parameters must be learned when using dot product? If we do this like computation, any models parameter computed, you can think of it like pause the video and try to think of it, okay? So for the dot product formulation, we simply multiply one vector by another element, okay? And so here we just sum the result, and which means that there are no weight matrices, there are no trainable components, and there is no transformation being applied. So because of this, like the dot product introduces zero learnable like parameters, okay? Means there is nothing to learn in this case. Here, like we do not have any parameters to learn. So it's like purely kind of computation or mathematical like operation which is applied to the input vector. Now, when it comes to the bilinear model, the question again, like how many parameters do we need to learn? Okay, so let's answer this question. You can try to answer. Okay, so here we say that we introduce this like matrix of weights, and these weights are going to be learned during the training process. So they are going to be updated. So these are the parameters, okay? So the only component that must be updated during the training is this weight matrix W, okay? So the bilinear, like, let me say, method or similarity metric, okay, form what we say like or introduces, let me say, one learnable parameter matrix, okay, which is, let me say, is adjusted through the training. Now let's move to the next one, which is the multi-layer perceptron, okay. So when it comes to the MLP approach, what we have here, we have two learnable parameter matrices, which are like W1 and W2, okay? So the key takeaway here is like if a vector, or let me say a component, cannot be modified or updated, such as like, for example, here, the red and the green like vectors, in this case, they are not changing at all. So we cannot consider that as model parameters, okay? These remain fixed, and let's say they are not learned. Now, for the weights matrix in blue now, these are updated during the training process. And so in contrast now, here what we have, the weight matrix, we have two, and they are like used inside the similarity function. They are updated during training, and therefore they qualify as, let me say, model parameters. So dot product has zero parameters. The bilinear now has like one parameter matrix, and the MLP version, let me say here, includes two parameter matrix. Perfect. Now, let's assume this part is complete. For each input, we have computed already a similarity score. Let's think of that. And this score reflects how much influence that input should have on the final prediction, okay? So what will happen? So to use these scores, let's say in an effective way, okay? What we will do, we need to kind of concrete numerical values. So values that when summed, they must be equal to 1, okay? Probability values, let's say. They can be interpreted as probabilities, okay? So This is why mainly we apply the softmax like function here, activation function, after computing these scores. Okay, so from these scores, we are going to have probabilities. And so because softmax converts, let me say, raw similarity values into proper like exact probability values between 0 and 1 that we can interpret. Okay, so it's so the higher is the probability values means that this score is let's say more important. Okay, so now once softmax is applied, now what will happen? Again, think of it. We're applying softmax. Simply, we are obtaining the probability values for each score. So a higher probability values closer than 1 indicates that the corresponding token is relevant. Okay, here comes the attention maybe. If we have lower probability values, that means the opposite. Yes, so the token carries kind of little importance. Little common filter words such as, for example, if I have sentence, he loves to eat, 2 in this sentence. It must have a very low probability value. So what does that mean? If we interpret that low probability values. Low probability value means that this token contributes minimally to the meaning, okay? So it gives you an idea about the contribution of this element or token to the overall meaning. So now we have the final attention weights, which quantify the influence of each token on the prediction. Perfect. Some tokens, like we said, have received, let me say, like eat here, higher weights because they are important, while we have others, maybe they receive lower weights, like because they contribute very little and with some, let's say, moderated weights and so on. So what we do next is that we combine them with the corresponding value vector to form the final representation. Okay, so this is the main idea. Now, what we have in here, we have this at this step. So we repeat the process for each time step. So what happened at each decoder time step, attention weights are computed that determine each input's relevance to the prediction. So once these scores now here are like computed, okay, the idea is like the softmax is going to produce the final probability distribution, like I said, and this is going to allow us to interpret the weights in a meaningful way, okay? Then, like what we have next is at each decoder time step, a prediction is made based on the weighted sum of the inputs, okay? So here, before using the weights, we move, and by the way, by moving here we move to the decoder part. So this is related to the encoder part, okay? So at this level, decoder part, what we will do, like the role of the decoder is to combine, I would say, like here, the weights information that we are getting and computing so far and generate the output, okay? It's going to be generated like based on that, okay? So the idea is here is at each like time step, okay, a prediction is made based on the weighted sum of the input representation. This is the main idea, okay? This weight sum now incorporates some attention, okay? So these attention values, I would say, are going to determine how much each token contributes to the final output, okay? So mainly this is the idea. So at this process, like the idea is like this process mainly is summarized in this like formula that you can see. So, and this idea or this formula mainly combines the attention weights, okay, with the value vectors in order to produce like the final prediction. So now something else is very important to note is that this final prediction that we have here, so involves three elements, okay? So we have the input word, okay, the previous state, and the context vector, okay? These are the three elements. Now for the input word, okay, so the input word is, let me say, at the current decoder time step, what input like word we consider, okay? The previous hidden state, mainly here, this hidden state carries the information from earlier output, okay? And for the context now vector, it is, let me say, the weighted sum, or the weighted sum is produced by the attention mechanism, okay? So these three elements, okay? So these three components now together, so what they will do, they are going to generate the next prediction, okay? And now the question is changing. The question becomes, how do we combine these elements? Okay, how do we combine them? So we can combine these three elements in different ways. So for example, we can maybe sum them, okay? We can concatenate them as well. We can consider taking the mean as well. So we have several options, okay? But the essential point mainly is that we must combine these three components in some way or some form to produce the final output representation. And now something remains unchangeable, let me say, okay? For each decoder time step, or what is it? So what stays the same, let me say, at each decoder time step, okay? This mainly a question that we can think of it at this level. You can pause the video again and think of it. So what does not change here? Something that is not updated, okay? So here, what is not updated is the input's hidden state, okay? Because the input hidden states now is not changing. Why? Because in the start, if we are like embedding that and encoding that, that remains unchangeable, okay? And so about the input, it's because like the input is having a representation, and this is like the input hidden state mainly. This is the main idea. So which is the result that we say we are obtaining from some RNN, we are obtaining from some LSTM, or whatever the technique that we are using, but we are obtaining the input hidden state, and that is final. That is not changing at all, okay? Now, maybe, let's say, whatever. So the answer is that the input hidden state is unchangeable. Okay, maybe we can have another question. Keep this answer in mind. Okay, what changes now at each decoder time step? The other hand. So now what changes? So the input now hidden states, they are fixed for now. They are not going to change. What will change is, pause the video, guess what? Great. So what mainly changes is the decoder hidden state and the attention weights and context, okay? So now the attention. Now the attention mechanism becomes, let me say, the first key step to understand. So we essentially are moving from the human idea of focusing on specific parts of the text to how this process actually takes place inside the neural network or a neural model. So particularly we're discussing the example of machine translation, so where at, let's say, each decoder time step or step, the model computes the attention scores. Then the decoder is going to identify which input tokens have the highest impact and that are going to most strongly, let me say, influence the final prediction. All components now in this process must remain differentiable. It's very important that which allows the entire system to be trained end to end using Reddit. So this is mainly summarizes the core idea of attention. So now by incorporating attention, like the network now is, let's say, no longer limited to relying slowly or only on the LSTM. So with the attention mechanism now, what we have is like as shown in this plot, even when the sentence like length increases, in this case, for example, the model's performance measured like by the blue score we discussed so far does not decrease, which is excellent, okay? So this demonstrates the effectiveness of attention, where let's say the model maintains high performance for even longer sentences. And it's very important to know that the performance here is no longer dropping. So if even you have the long sentences, still we have good performance, which is excellent. So now this does not only improve performance, okay? So paying attention also makes the model, let me say, more interpretable. When I talk about interpretability, it's mainly we are understanding or explaining very well the model. So attention can allow us to understand how, for example, these, let me call them black box models maybe, take decision. So because if we introduce attention now, there is a focus, there is an attention, okay? So let's consider these two heat maps, okay? And in this case, they illustrate clearly this idea. So what we have is that we have these two different sentences, okay? So for the first one, the agreement on the European Economic Area was signed in August 1992, okay? And so in this sentence, the word, let me say, token having most importance is 1992, which makes sense because this sentence is mainly giving you an idea about the date. Okay, so it's clear. So here you having the lighter points. They show the more or the higher, I would say, attention values. Okay, the same for this one. Okay, so we have higher attention here. Okay, so this will change my future with my family. Okay, the man said. So the man said here it's not that much important, but change my future with my family. It's these four tokens are extremely important. We can see that. Okay, so this is very important because like I said, like the model identifies the most important information, like the date, like for example, the keywords in the sentence and so on. Okay, so like this way we can visualize the values. And by the way, these values are shown in grayscale, and we have white and black. Maximum is 1 and the minimum is 0. So their values between 0 and 1, and they are indicating how much attention is the model like giving to each input word. So attention is useful and attention is nice. Let me say attention is great, but before introducing attention, it's important to revisit the idea that led us there, okay? So we begin with recurrent neural networks or RNNs. When, let me say, we think of, let me come back to CNN again, convolutional neural networks. The association should be automatic. So when I say CNN, usually many of you will think about feature extraction, extract features from input. These features are computed through convolutional layers, and then they are like passed to classification part. When we talk about RNN, you must think of like different ways. So you need to this introduces different concepts, okay? So when I say RNN, you must think of memory and time, okay? Because it introduces memory and time. So instead, like of relying on convolutional neural networks, here RNN, they operate through hidden states, okay? Each hidden state in this case like carries information, okay, from previous, you have for example, ST, this state carries the information about ST minus 1, which is the previous time step, okay? ST plus 1 carries the information about ST. And so here, by introducing like this concept of time steps, we allow the model to learn patterns that I would say unfold across time, okay? So this brings us like the idea of sequence processing and temporal dependencies. So while this mechanism is powerful, it also introduces several limitations, okay? So let's discuss. So the thing is that as the number of time steps here increases, what will happen? The RNN is going to encounter problems such as we discussed the vanishing gradient problem, the exploding gradient problem, and increasing computational difficulty also as the sequences they grow longer. So these challenges mainly affect both training and inference, which makes it harder for the RNN to capture long range dependencies, or let me say handle large output efficiency. So the natural question becomes, what kind of solution can replace recurrent neural networks if they have this kind of limitations? And in this case, let me say that the obvious direction means, let me say, to avoid using RNN. Like if that vector S before is creating a problem, let's not think of it. Let's think of attention. Now RNN are making problem. What we'll do? Okay, let's not think of them, and let's replace them. Okay, so one option is to replace the recurrent neural network with sequential hidden states. That's a way. That's possible. So the idea here that sequential hidden states capture information from all the input through a new representation. So in this case, one that can reflect each token's relationship to every other token, okay? In the sequence, of course. So this leads to the idea of using self-attention. So self-attention is when, like, instead of recurrent neural networks, if self-attention provides such strong performance and interpretability, let's say, then the next step is to explore how we can use it as, let me say, a complete replacement of RNNs. Very interesting. So just be careful here, okay? So earlier we introduced the concept of attention, okay? Attention, here we have hard attention, and one by one, for each time step, we are paying attention to each token from the input sentence. Okay, so specifically in the, let me say, side where attention is applied here, in this case, I would say across different parts of the input at each time step. So we need to like be careful, because this is what we discussed earlier. Okay, so this method is not the same as self-attention. Okay, so this is attention, which has its limitations. Now, self-attention is something else, so it's different. This is what I want to pay your attention to, so be careful, okay? So self-attention mechanism is different, and we are about to discuss, so you will discover this. The idea of attention is already covered, okay? It's already clear for you, and it's the following. So at each time step, what will happen? The model focus at a particular part of the input, okay? And for example, here, first time step, we focus on the first part. Second time step, we focus on the second part. Third time step, we focus on the third part. Last time step, we focus on the last part. So what will happen now? You can this is mainly the idea. So you can follow this behavior by looking like I will just show right here, the orientation of this going from the target to the input, sure, okay? The arrows in this diagram. So this is classical attention, okay? Now I am going to discuss self-attention, okay? So get ready for it. How self-attention operates. Here we go. Okay, this is self-attention. So just seeing the graph or the diagram, you're going to understand things, I'm sure. So the difference is that with self-attention, each token, let's think of bank in this case, each token attends to first itself and to every other token in the sentence, which is great. So instead of moving, let me say, step by step and focusing on, let me say, one part or one time step and look at the other element, what we will do here is that we do things simultaneously. So visually, the distinction is clear, between the classical attention and this self-attention, and also the focus, it shifted, okay? So it shifted, I would say, across positions in the classical attention. For self-attention, it allows, let me say, a single token to connect to entire sentence, okay? So now let's return to self-attention mechanism, okay? And the idea here for each token, like I mentioned, to consider itself, the relationship, with itself, and the relationship with every word or every token in the sentence, okay? And this is the core idea, okay? Like I arrived at the bank after crossing the river, okay? Bank to each of these words, okay? So this is mainly the global view of that allows the model to capture rich contextual meaning for each token. Okay, now after applying self-attention, we examine the resulting attention weights, okay? So these weights differ, I would say, for each token, depending on how relevant every, I would say, word or other word is to the current one. So in the diagram here, what we see different sizes, I would say, of these arrows. So we can have some thick, the thickness of the arrow represents the strength of the attention weights. So the token, let's say bank here, okay? With this one, the model assigns varying, I would say, level of importance to the other word in the sentence. So words like bank and itself, for example, in blue, we have bank and arrived in green, it's less attention. But bank and river now here, it has more, I would say, important weights. Okay, so the arrow thickness indicates the attention of the weights, and the one here in red shows now let me say, the correct contextual meaning and the relationship between the word bank and river, given the self-attention mechanism that helps, I would say, the model to interpret ambiguous words by connecting them to the most relevant, I would say. Now again, focusing on bank and river here. So a large attention, like I mentioned, like score indicates that the other word will strongly influence the new representation of the current token. So this shows the influence of the word river on the current word bank. So in other words, if I have a high score reflects strong correlation, we're talking about correlation so far, between two words, and this correlation shapes how the model mainly encodes their meaning. So now the question becomes, I would say, given the sentence like I arrived at the bank after crossing the, let me think of it now. I have 3 dots. So let's assume like the part of the sentence is missing. How should the model interpret, I would say, the word bank? Okay, so if we consider this part is missing, what does bank mean in this sentence? So because previously we've proven that this is the strongest correlation. What happens if this is not there? Okay, this is mainly the question. Okay, just you can pause the video again and you can think of it. The answer is simple. So mainly, okay, simple, but still you can think of it. Okay, so the answer is the meaning of bank here mainly depends entirely on the missing context, right? So the question now is, if I have the sentence, I arrived at the bank after crossing the, and the final word is missing, how should the model understand bank? The interpretations mainly depends entirely on what comes next, okay? So let's take the example with the missing part. Okay, a missing word could be filled with anything that is contextually valid, such as we can add here the word river. That's possible. We can even say street. Okay, that is also possible. Okay, so again, with this like completed sentence, we ask the same question. What does the word bank mean in this context? Okay, so in this context or in this context. Okay, so now the new representation of the word is mainly influenced by the relevance and also by the impact of the surrounding tokens. So if the missing word turns out, I would say, to be river, then the attention weight between bank and river will be high. So now, shifting the meaning, this is mainly shifting the meaning towards river bank. So this is exactly how systems perform this type of tasks, where mainly it's treated as auto-completion, okay? So as you, like, for example, what kind of example? In your phone, you're going to type and it's going to suggest you some auto-completion. You can think of that, disturbs everyone. So now the model is, you type and the model uses self-attention to determine which word is most likely to follow based on the learned, I would say, relevance pattern, okay? This is the idea. So now, whether the missing word is street or river, and that mainly depends entirely on the meaning conveyed by the rest of the sentence. Like if, let me say, we rely on traditional RNNs, the model cannot determine the meaning of bank immediately. So it has to wait, process the entire sentence step by step, and only then, like, it can decide, because RNNs do not have access to all tokens at once. Okay. However, now with transformers, the situation is different. Okay. The model doesn't need to wait for full, I would say, input. It can predict or infer the meaning directly because it can see all the words simultaneously. So when we say it can predict, we mean it evaluates every token in parallel and, let's say, use self-attention to establish relationship instantly. So this is the key distinction, I would say. Transformers access the entire sequence at once, while RNNs rely on sequential processing. So now let's dive into self-attention and in more details. What we are computing here is mainly new representation for each token in the sentence. So one that captures its relationship with all the other tokens, let's say. So for every word now, what we will do, we are going to generate, okay, um, like an updated vector, okay, that reflects how strongly, I would say, it is connected to every other word in the sentence. So mainly this is the idea that we will discuss for self-attention. So new representation of each token in a sequence is going to show like how this like relationship and connection to all other tokens. So this is an example. We have here Rashanda accepted a job in deep learning because she loves the topic. Okay. Now, if we start with the like subject, which is Rashanda, what we do, we compute the self-attention, okay, or that of that token. This makes like this means that we evaluate how Rashanda relates to Rashanda and then to each, I would say, token in this sentence, okay? And how it will happen mainly by assigning weights to all of them accordingly. And based on this, we can determine the relationships between the token and the rest of the sequence. For example, in the case like, for example, of if like she, like the model learns strong relationship, okay, or correlation with words like, for example, accepted, or she, okay, Rashanda, or she accepted. So here there is a stronger correlation, okay, with the between the verb and the subject name. Since this, like here, she about Rashanda, okay, so this she mainly refers to the entity in this sentence, which is the first one, which is the first token, I mean, Rashanda. So the longer the sentence becomes, the more relationships we need to explore. And in this case, like the sequence grows, self-attention must evaluate in this case how each like token interacts with all the remaining words in the sentence for all of them, okay? So what we will do next, now we finally plot the self-attention results. So here is the final plot, and we observe like that the token she in this case produces a better representation like for encoding the meaning of the name Rashanda, okay, in this sentence. So to just the model learns that she refers to Rashanda, and the attention weights as a result here, or the main reason, let me say, reflect this connection, okay? Just to illustrate. This is why here you can see that it's thick. The same idea here also applies to the earlier example with river. So here river provides better representation like of the word bank based on like the relationships with within the sentence. Okay, so now we can, let's say, compare two approaches. We can compare self-attention to general attention. Okay, so this is self-attention, this is a general attention. So In self-attention, what we have, the relationships are computed between tokens from the same source sequence, and each token looks at all other tokens which are within the same input. However, on the other hand, what we have here, the case of general attention, it mainly relates, let me say, tokens that are coming from different sources. Like, for example, the encoder-decoder attention, we rely on the encoder features, the previous hidden state, like in the decoder, and the similarity measure between like them, okay? So these components together determine like how much each encoder token contributes to the decoder current output. So now what we do is, how do we compute self-attention? Now we are distinguishing it from attention, or how to compute that. So the mechanism mainly follows the same idea we have been discussing. So the key difference is that we must consider both input token itself and the attention score. So this score is, let me say, multiplied by a value that is, let me say, derived from the input, and that's mainly given the weighted contribution of the like each token, okay? So the mechanism is similar, with the main differences coming from the nature of this method. Self-attention is fundamentally different from general attention, but the overall structure for computing it like kind of remains the same. So the computational is this like structure is the same. We only adjust the components related to encoder features, the previous hidden state, and the method used to calculate similarity. So this example here illustrates the idea. So here we have 3 input tokens. My laser is not working now. Okay, so here we have 3 input tokens. From these tokens, what will happen, that we are going to generate like new representations that express each input like a relationship with others. Since now we are using the self-attention mechanism, so every token must reflect its connection like to all remaining tokens in the sequence, okay? And so this is the key difference. So in this example, we have 3 input tokens. So let me ask about the dimension of each input tokens, okay? Pause the video and try to think about the dimension of each like token here. 1, 2, 3, 4. Okay, so we have 3 tokens. Each token is having the dimension 4. It's straightforward to see. So for each input vector, we have 4 components, and the dimension for each component is as simple as 4. Okay, 3, 4, 3. Okay, now what we will see is the self-attention computation. So we generate 3 vectors, okay? And these 3 vectors mainly are the query, key, and value. So the colors here, they have like kind of significance. So try to use that, okay? So, and now to obtain them, what we do is that mainly we multiply the input token, okay, with this is the input token. We are going to multiply the input like token by 3 different parameter matrices, okay? So one is the query, one is the key, and one is the value, okay? All these parameters are learned during training, okay? So they are going to continuously be updated and refined, okay? Keep that in mind. So now this is going to happen for each input token. And so for each of them, we're going to produce a vector and value vector and key vector, okay? For each of them, for each like token, we have three vector: key, value, query, key, value, query, key, value, query, three. Okay, good. Now, an example of a key is shown here, okay? So it's simply a matrix that is containing learnable weights. Okay, so these are the weights that are going to be changing and during the training, okay, until converging. So similar to the weights that we are familiar with in CNNs or other neural networks, okay? So, and what we do here is that we multiply the input token with the key matrix. We multiply them with the value matrix, and so we obtain, what we obtain is mainly the query. Okay. Once we have this information for each like input token, so we have the key, value, and query, okay, we generate these three like matrices, one for Q, one for value, one for and one for query. These matrices contain the learnable parameters that will be used to compute the self-attached. Okay, great. So what we have, these three like weighted, I would say, matrices are learned through the training process. I'm repeating this again and again because it's very important. So at this point, you might ask yourself, why do we learn them even? Okay, I'm saying they are like learned. Why they are learned? This is a very important question. So the answer is very simple. It's because updating these weights allow the model to identify which features are most important and how each token should like contribute to the final representation. Okay, so as easy as this answer. And now what we will do is that we're going to begin with the first like we're going to begin processing the first input, and so we are going to treat them one by one, okay? But let's start with the first input token. And at this stage, what we do consider is only the first input token, which means that we do not consider the other two. Well, how we will do now? Now we are going to take the key like vector for the first input, and we are going to multiply it by the corresponding query vector, okay? And so to perform this multiplication, we apply the dot product operation. How it works? So we multiply 1 by 0, which is equal to 0, plus 0 by 1, which is equal to 0. So we have 0 plus 0, plus 2 multiplied by 1, which is equal to 2. So here the result is 2. Okay, so for this one, for the first one, we computed, we found 2. And they'll keep going, doing the same thing. So means we multiply the query with the key for the second one. So we obtain in this case, so 1 multiplied by 4 equals 4 plus, so 4 plus 0 plus 0, so it's equal to 4. So previously we had 2, now we are having 4. For the next one, we'll do the same, multiply like the query by query is this one with the third key. So the key is having values 2, 3, 1. The query is having 1, 0, 2. So the result here is going to give us again 4. So the final similarity values now that we have for this example, like I mentioned, they are 2, 4, 4. So we compute these dot product scores in order to build the similarity matrix we have been discussing so far. So don't forget that this matrix captures how strongly each token is related to others. And here we see that, like as we said, so a very simple way to use is to compute the similarity matrix using the dot like product. Okay, so we are going to use the dot product because we mainly mention also that this one does not introduce any weights or parameters. Remember? Okay, so we can use maybe the bilinear if we think about parameters. So we have only one weights matrix, which is W. Can think of the multi-layer perceptron, which introduces two matrices of weights. And so here, how I am going to choose, okay? So this is the question. So I was mentioning that in general, like the people in the literature, they try to avoid using the similarity matrix that introduce many weights, okay? So here we have two weights. And so very simple one, let's say that is the introducing the dot product, because using the dot product because it does not introduce any parameters, at least at this level. Okay, so this is the mainly one. So in this case, we're going to use the dot product for our similarity metric. So this metric mainly reflects how strongly two vectors align. So values, like I mentioned, closer to one indicate like strong relationship or higher relevant features. Yeah, and vectors which are like closer to, let's say, 0. Okay, here we can think of -1, okay, because we are going to use the opposite, okay. So if they're closer to -1, then this alignment score helps determine how much influence, let's say, one token have like on another, like if I would say self-attention is used. Okay, so here just I want you to know that we can also use similarity measures other than the dot product, okay? Just selecting that for simplicity. So now, although other similarity metrics can be used, we are relying on the dot product. So at least for this example. So after computing the dot product values, now what we do, so we do not have probabilities. How to get probabilities. Now what we are having are values between 0 and -1, okay? Now what we need is probability. So to convert these values, okay, between -1 and 1 into meaningful weights, we apply the softmax layer, which transforms these scores into values between 0 and 1. And with the total summing here, we must find total is equal to 1. So we had 2, 4, 4. We apply softmax function. It's giving us this 0, 0.5, 0.5. And these are the attention weights that we have computed. Good. Next, we are going to multiply these attention weights with the values. And as a result, now these are like the result of multiplying the attention weights by values, we will have these like weighted vectors, okay? So here, the weighted vectors have zeros somewhere. So 0 here indicates no importance, okay? While, for example, 4 here, let me say higher values, they represent stronger relevance. Here I have 1, so there is stronger relevance, okay? So these results means at this level are easy to interpret. So some positions contain meaningful features, while others, like the first one, for example, contribute nothing, I would say. So using these weights, we obtain a weighted representation, okay? And in this case, the important like tokens are amplified, like in the middle here. This one is very important, it's amplified, okay? So the important ones are amplified, and the unimportant ones are maybe suppressed. So the model can now pay more attention to certain elements while giving little or no attention to others. So this selective weighting allows the network to focus on the most relevant parts of the input. Good. So we're going to repeat the same process for each like remaining input token, okay? And here, like for example, we'll do for the second query. In this case, we don't consider the first and the third or last query, okay? So we compute the attention weights, then we compute the weight sum of values using attention scores. Now next we move to the third query. We don't consider the first and second queries, and we do the same. So compute attention weights and like from query here dot product keys, compute the weight sum of the values using attention scores. So we keep doing this for all the like tokens that we have, and until like at the end we are going to have our final like weights, okay? So this example is very simple, basic, I would say, but effective. And it demonstrates how self-attention works and the reason why it is useful mainly. So let me say contradiction now that self-attention can be made more efficient, okay? Even that it's now simple, perfect, let me say, but it could be more efficient. You can like think of what kind of improvements maybe can we introduce here. So can pause the video and think. So in this step, for each row of the input token, maybe what we do is that we are considering, or maybe we are mainly producing one attention weight and one like query weight. So the idea is just we have just one single, just a single perspective on the relationship. So now think of something we covered so far. In convolutional neural networks, for example, it's my favorite example. So what do we have there? So in CNNs, what we have mainly, we introduce the idea of multiple filters to like extract different types of features. So here is the same idea. So we are going to introduce multiple self-attention like mechanisms. So each with its own like key value and like query. And our goal is that we enable each token to relate to other token like multiple ways. Okay. So mainly what happens is that we're introducing multiple filters, okay? Instead of multiple filters, sorry, multiple head attentions, okay? Moving from simple self-attention to multiple head attention. So the input cannot be changed again. So this is why here X remains unchangeable. And so what we can modify maybe here is mainly the weight metrics and the key query and value, okay, vectors. So by increasing the number of these weight matrix in this case, it's going to result in increasing number of keys or set of queries and values, okay. So the goal is to allow each token to relate to other tokens in different, or let me say multiple ways as the same time, okay, at the same time. So this is mainly achieved through multiple self-attention, okay, and now mainly this mechanism is operating, let me say, in parallel. So this is known as multi-head attention. This is why it's called multi-head attention, because it's running in parallel, where each head, let me say, has its own query, it has its own like key, and it has its own value. So if we now visualize the full architecture of multi-head attention, we see three main steps. So the first step mainly is that we generate key and value vectors for each attention head, okay? Second, each head computes its own input okay? The input representation of sure by applying the self attention in parallel. And finally, we condense these multiple representations into single output, only one output at the end that we will have, and this mainly by concatenating them and then multiplying by the final weights. So now let's summarize again how attention is computed, okay? Just like to understand overall concept. So how it's implemented is a very important question. So first, when we discuss it in basic attention and self-attention, this was our starting point, and then extended to multiple heads. So this idea is the same. We multiply the input, okay, by the weight matrix, okay, for the query, okay, and next what we'll do, multiplying by the weight matrix for the key, multiplying by the weight matrix for the value. So here we obtain the the key, sorry. Here we obtain the value vector. So once these vectors q, k, and v are computed, what we will do is that we apply same logic which is used earlier, okay? So what we do is each head behaves exactly like, for example, extracting one feature in CNN. So by using different weight methods, we obtain multiple keys, we can obtain multiple values, we can obtain also multiple Qs, okay? So this is the same idea of filters in CNN. And next now, once we obtain here the values that could vary between -1 and 1, what we do is that in order to interpret that or translate that into probability values between 0 and 1, we need to apply the softmax activation function, okay? So mainly this is the idea. And to summarize also for the multi-head attention, the first step is to create query, key, and value vectors for all the attention heads. Next, we compute new input representation. So finally, we condense all representation into a single representation by concatenating these and multiplying by weight matrix. Good. So now let's talk about one of the biggest differences, I would say, between RNNs and transformers, okay? So in RNNs, information flow, here it flows step by step, okay? And the idea is it goes through a recurrent unit here, for example. And this loop is what allows RNN to remember past information. But the problem now is it makes learning slow, sometimes unstable, and it struggles with long range dependencies. Okay, so now for transformers, we remove this entire recurrent structure, so we don't have it anymore, and we completely let's say cut the loop. Fine. So instead of the use of that, so mainly they use something more powerful, which is self attention. Okay, so here you can see an example of self attention. So we have the cat sat on V, and so here we have missing points. We can try to fill in the blanks. So this can directly look at every other word in the same time. Okay, this is how it works. And no recurrence, no step-by-step processing, just the model asks which word should I pay attention to when understanding this word. Okay, so this ability connect all the words simultaneously, this is the power, and is and this is mainly the reason that transformers they learn faster. Okay, they handle long sequences better, and they become the foundation of modern models like GPT. Okay, just to summarize, transformers are based on self-attention and multi-hit attention. Self-attention is the core mechanism that allows the model to weight the importance of different words in a sentence when encoding given a word. The multi-hit attention is an extension of self-attention where multiple attention mechanisms or heads they run in parallel, capturing the different contextual information and enhancing representation learning. For the transformer architecture, primarily relies on the self-attention and multi-hit attention to process input sentences effectively. So I try to summarize everything in this slide. And I think that we in this video covered the foundation to understand the transformer architectures. We understood how attention works, how self-attention works, multi-head attention, and now we are ready to explore in the next video transformers. And again, the engine behind today's most powerful generative AI models. Thank you for watching.